Good morning. I guess I'm good to go. Good morning. My name is Giorgio Clauser. I lead the data team at Moneyfarm, one of the most important firms in the digital investment space in Europe. And today I will walk you through Explainability Explained, from data coefficients to SHAPly values. Before we get started, I want to give you an overview of the agenda. So we will start with the importance of explainability in machine learning, seen by the angles of behavioral economics as well as regulatory requirements. We will then briefly touch on the concepts of global and local explainability, and we will move on with the traditional statistical models case. Moving forward, we will touch upon the contemporary machine learning models case, focusing on their mathematical complexity, and finally addressing local explainability with SHAP. I will then conclude by sharing a case study from the experience of my team at Moneyfarm, how we embedded SHAPly values in production output, and review, of course, the pros and cons of the SHAP approach. So now, to kind of set the mood, I'm gonna ask you to imagine that you apply for a credit card loan. You know it, you are data scientists, you are machine learning engineers, your application will be scored by a machine learning model. And now imagine that your application is rejected. If you visualize yourself in this situation just for a moment, I'm sure there is one single question that comes to your mind. Why? Why was my application rejected? And it's not enough for you to know that you received some score and that score did not meet some threshold. You want to know kind of, what did I do wrong? What's wrong with me? Is it my salary? Is it not big enough? What's wrong with my application? What's the inner cause of my failed application? So just from this kind of psychological experiment, I'm sure you will agree with me that the output of predictive models should be explainable. And I am very, very happy to spend one moment to go deeper on this concept from some angles that we probably as technologists do not often look at. A topic that I really, really like is behavioral economics. And let me introduce you to this guy. His name is Daniel Kahneman. He's very well known because he won the Nobel Prize, and he wrote an international bestseller called Thinking Fast and Slow, where he condensed all of his knowledge that granted him the Nobel Prize. Amongst his theory and amongst his theory, he calls the human brain something like a machine for jumping to conclusions. And he tries to explain a lot how we strongly need causal explanation for everything that happens around us. So he would say that our mind is biased toward causal explanations. He would say that we have a predilection for causal thinking, and this exposes us to making mistakes in understanding what happens in our life, because causality is not there by design in everything that happens around us. He would also say that we are pattern seekers. We need to believe that what happens around us is the result of mechanical causality. So I know these are just a few quotes from a book, but it's kind of to justify that the need to build a causal narrative for decisions that are done and that concern us is inbuilt in the human brain. And this is why we as humans feel that machine learning models should be explainable. Now, another angle that is very, very important is the regulatory requirements. I'm Italian, I'm European. In Europe, we like our regulations very, very much. And let me give you two examples. We have something called the GDPR, or General Data Protection Rule. It was voted on the 25th of May, 2018. And this regulation contains something called right to explanation. So it clearly states in an official European Union regulation that the individual has a right to explanation when it comes to decisions made on the behalf of the individual by an automated system, so by a machine learning model, by an AI. So right to explanation is embedded into regulations. Another very interesting regulation, more recent, is the EU AI Act. It passed on the 13th of March of this year. And once again, even in this document, which is huge, and you can find it on the internet and explore it if you want. But there are so many references to explainability and transparency of the AI systems. I'm quoting here two examples. AI systems should allow appropriate traceability and explainability, and at the same time, they should have the technical capabilities to provide information relevant to explain its output. So if I did not convince you with the behavioral economics, at least in Europe, now you cannot really think to build AI stuff, to do machine learning without being able to explain what's going on in your models. So now that we know and we agree that it's very important for a number of reasons, let's get into it. Let me present you the use case that we will be using in the next 10 to 15 minutes. Very simple example, we will be predicting the churn risk for a main customer. So we have a data frame with a collection of features, age, account balance, digital engagement, product number, and estimated salaries. And we will try to predict the churn, which will be our target variable. Of course, this data set, we will consider it as a data set as a whole, but we will not forget that this data set contains information about individuals. It contains information about Mark, a 56 years old bank customer with 112K account balance. So one of our challenges will be, through our models, being able to say something about Mark. Moving forward, a quick recap on global and local explainability. We probably all know this, but I think it's important to set some common ground. Global explainability, that means providing an overall understanding of how a model works across an entire data set or population. So something very general. The model predicting churn risk reacts to age and digital engagement. And we all agree this is easy. We have all experienced it. Local explainability is something different. Local explainability means we are able to talk about Mark. We can explain the individual prediction and the individual decision made by the model for a specific data point. For Mark, Mark's risk is a result of his 56 years of age, a result of his high estimated salary, but big balance, etc. This is hard, and this is the whole reason why we're here today, I believe. So now that we have this clear, we can jump to one of my favorite topics, traditional statistical models. So let's get into it. The headline is that global explainability and local explainability is the same when we work with traditional statistical models because they are both based on the data coefficients. So what happens when we train, for example, a logistic regression to model the churn? Because it's super easy. The stats model package from Python does all the magic. We get this output that looks very ugly. You cannot present it to a business stakeholder, but as a statistician, I really love it because it's like doing an X-ray and looking inside of the model and understanding exactly what's going on. In particular, we have the set of coefficients. We can just read the coefficients and we will have the global explanation of the model. Constant is negative, therefore churn risk is tends to be low by default. Age has a big positive coefficient, therefore the older the customer, the bigger the churn risk. Balance, positive coefficient, positive correlation with the churn risk, and digital engagement brings the churn risk down. So global explainability, done, easy, by X-ray on the model, provided that by the estimated beta coefficients. When we go to building an individual prediction, the amazing thing is that we basically have an equation, like in this case where sigma is the logistic function, that builds up the individual prediction using the coefficients estimated by the model. And they are the same coefficients, it's the same thing. And when we look at the churn risk predicted by Mark, you can explain it exactly with the same coefficients that explain the whole model. So there is no doubt what drove Mark's prediction. This set of coefficients, and they are the same for every customer, and the EU AI Act would be happy because we are completely able to explain this prediction for Mark or for any customer. This is why traditional statistical models, generalized linear models, they do not perform as well as the most recent models. We all know this, but they are still market standard in highly regulated environments such as insurance. If we think about it, the traditional statistical models, they blossomed in the 70s. I put here for you a cornerstone paper that generalized linear models from somewhere in the 70s. And this is what a computer looked like in the 70s. So for as much as it would be fun to work with these machines nowadays, that's no longer how the world is. So let's move forward, and let's talk for a moment about contemporary machine learning models. Remember, we just did an X-ray on the logistic regression. We were able to see the coefficients and look at how the whole system works. Let's try and do the same for a tree-based model for tree ensembles. We'll like to import like XGBOOST, import XGBOOST, and then run our predictions. That's very fun, very easy. But what is really happening under the hood? We have a target variable y that we try to estimate as a function of the features x. And in this case of tree ensembles, this is what the function of the features, the f of x, looks like. It's the sum of theta times h of I, where h is the decision tree. Now we have a formulation for a decision tree, which it's starting to look not so nice to work with from a mathematical point of view. We can still manage, but it's starting to become difficult. When we look at the theta coefficient, that's actually the gradient optimization term, and this is really difficult. It's got multiple components, partial derivatives. It's really difficult. We have a part dealing with the loss function, and clearly the option to X-ray the model and look exactly what it is doing, how is it building its decision, is no longer possible. So math makes things very difficult for the tree ensembles. And from time to time, it's good to look at this reality item in the face directly from the equations. The good news is that for the global explainability, we still manage. We have all the packages have the feature importances or similar function, and we can get something like this, like the split feature importance, that is based on how frequently each variable splits data in the trees that are part of the ensemble. It's telling us that the model reacts mainly to the balance and the age of the customer. But if you really think about it, compared to the traditional, to the logistic regression, it's bad, because this is only telling us that the model reacts to balance. It doesn't tell us if in a positive way, so if the correlation with balance brings the churn risk up, or if it brings it down. Moving forward, local explainability, which is what's really interesting. That's super hard in the context of trees ensembles because of the model complexity. We just saw the equation. To be honest, it kind of scares me. We have non-linearity effects. These models are able to capture cases where the churn risk correlates maybe with very young or very old customers. It's super cool, but again, makes things difficult. We have cross-up dimensionality. Dealing with hundreds of variables, it's pretty cool, gives better prediction results, but again, it's difficult. And we have the local context that kind of wraps up everything I just said. Mark's prediction might be driven from some variables, and Alex or some other customer's predictions might be driven by some other variables. All of these makes things difficult for trees ensembles. But in our help comes SHAP. SHAP is an approach to interpreting model predictions discovered or proposed in 2017, so really quite recent. I think it became something looked at in the industry around 2020, 2019, something like that. It's an algorithmic approach based on cooperative game theory, and it kind of works out how much a variable is important by measuring the marginal contribution to the final prediction that this variable brings by adding it and removing it from the model, and basically training all the possible combination of models adding and removing every single variable. We just saw a bunch of equations, so let's see one more. This is how SHAPly values would be generated for a Phi2J in a model with n feature for a given prediction. So again, the equation doesn't look super friendly, but I would say looks like something a bit more friendly than compared to what we saw before. Now, digging really deep into how SHAPly values work, I think it would require a dedicated talk. I'd much rather have a look how they work in practice. So let's try to explain max churn score using the SHAPly values. This is the starting point. As you can see on the right-hand side, couple of instructions, very easy, and we train a SHAP explainer, we compute the SHAPly values, and then we plot them. So really easy to use with a Python library dedicated. The chart on the left, it's kind of the peak, in my opinion, of what we can get with SHAP. If we look at it, we notice the expected value on the bottom, which is the average prediction in the whole data set, 0.2. So average churn risk is 0.2. Then we have f of x, which is the prediction for mark. Mark churn risk is 0.7. Then if we go to the bottom left, we have 93.9K, which is the estimated salary for mark. So it gives you the value of the specific feature for the specific observation. And the most interesting data point, the one that gives meaning to it all, is this minus 0.01, which is the deviation from the mean prediction caused by the estimated salary of mark in this observation. So if we go from the bottom to the top, analyzing these deviations, we will be able to fully explain mark's churn score. We start from a 0.2, which is the baseline prediction, the prediction that we would make without any information, without any feature. From 0.2, we go down of 0.01 due to the estimated salary of mark. Then we go back up of 0.04 due to mark's account balance. Product number bring the churn risk down. Again, the digital engagement is low. Everybody knows that when a customer does not have digital engagement, that's not a good sign. Brings the churn risk back up. But in this case, this model mostly reacts to age. So the biggest contribution to the churn prediction for mark comes from the age of 56 years. So really, I think this is the best you can get when trying to explain a predictive model using the SHAPly values. Now, I want to conclude by sharing with you how we solved at Moneyfarm the challenge of embedding SHAPly values into the production output of our predictive models. We tackled this challenge with the objective of enabling business stakeholders to deploy tailored commercial initiatives. So this was the kind of goal behind our work. First challenge was adapting the code base. Maybe it's trivial to say, but you need to add the SHAP explainer training to the training procedure. And then you need to adapt also the scoring procedure to pull the SHAP explainer and calculate the SHAPly values. Bear in mind, we will see it in 1 minute. A major refactoring of the format of SHAPly values will be needed. And once again, I want to remark, it's 2 procedures that you have to adapt: the training and the scoring, and make sure that you do it in a harmonized way. Otherwise, you might encounter problems. Another challenge that we had was to map machine learning features into business concepts. So imagine that you are working with a set of features like this. We have platform activities, so logins and views, but we look at them under many different angles. Android logins, iOS logins, web logins, in the past 2 months, in the past 2 weeks. We look at behavioral shifts. So we have many different angles on the same data point, but they all basically boil down to a single concept. Now, if we present 200 different data points to a business stakeholders, all saying more or less the same thing, they would not be able to make sense out of it. So what we did is mapping these features into business concepts. We achieved it by using a very simple approach, lookup table. But the thing that I want to mention here is that SHAPly values are additive. So you can calculate contributions of the concept you see on the right just by summing the contributions of related features. So this is an amazing property of SHAPly values that in our specific use case we found to be very useful. Last thing that we did is deploy some real pandas ninjutsu. What happens is that the SHAPly values, once you generate them, they have a terrible format, which makes almost impossible to work with outside of the SHAP package. So you get this collection of 3 arrays, and it makes no sense until you change the format. What we did, we added a column in the tables where we store our predictive model scores. We added a column that contains a JSON where for every business concept there is the associated SHAPly values. We achieved this by writing Python code, basically a collection of pandas, NumPy lists, stuff like that. And it's low-level code. I'm not going to go into the details, but if you ever embark on such a journey to add SHAPly values output to your predictive models, be prepared that some major refactoring of the format will be needed. This concludes the use case discussion. And before stopping, I just want to conclude: is using SHAP a good idea? In my opinion, yes, it is, of course. Otherwise, I would not be discussing this with you guys. But why? First and foremost, SHAP has a very strong theoretical foundation. It's based on the cooperative game theory, and you can really trust that whatever you produce is backed by strong theory. It provides both global and local explainability. We focused on the local part, which is the most interesting, but it's also very good at providing global explainability, addressing some of the shortcomings of the standard methods inbuilt in the machine learning packages. It's model agnostic, so you can plug SHAP explainer to XGBOOST, to light-running boosted, to anything, and it will work. And this is really great news. And last but not least, it comes with cool charts. So the one I demonstrated, the waterfall chart, it's by far my favorite. It's not the only one, and you can build more and more cool charts just out of the SHAP package. You don't have to use ChatGPT to adjust your charts using Matplotlib and Plotly or Seaborn or whatever you're using. The only downside that I see is that SHAP is computationally expensive. So generating SHAPly values will have you working with something in the dimension space of 2 power n, where n is the number of features in your data set. Currently, the SHAP pipelines in our machine learning pipelines for training and scoring, they are the component that takes the biggest portion of time, and you have to be mindful it will be computationally expensive. The SHAP Python package comes with already inbuilt approximation techniques, so you would not really work with 2 power n dimensions. It will do approximations, so the problem is half solved, but at the same time, bear in mind, it would be computationally expensive. So that's it. Thank you for your attention. Thanks to Open Data Science Conference for hosting me as a speaker. This concludes my presentation. I hope you liked it, and I will be happy to answer any question.
All right, thank you so much. We got a couple of questions coming in. The first one, given the GDPR and EU AI Act, any thoughts on using LLMs going forward and handling explainability?
Yes. Yes, I think LLM did not demonstrate to kind of be super friendly with the European Union requirements around fairness, explainability, etc. There have been a couple of cases where the output of ChatGPT was kind of involved in regulatory issues. So I would not see LLM plugged directly to a model in order to explain it. For sure, there is a strong use case in LLM to connect the dots. Imagine feeding the SHAPly values and the feature values to an LLM and asking this LLM to explain the prediction in natural language using those SHAPly values and those feature values. That would surely bring the explainability capability of a machine learning application one step forward.
All right, our next question is, how does SHAP compare to other feature explainability methods, like LIME?
To be honest, I cannot answer this because I have a very good knowledge of SHAP, but I am just getting started to explore alternatives. So I will run some research, and if whoever asks the questions wants to reach back to me in a few weeks, maybe we can have a conversation about it.
All right, I got a long question. It's a two-parter. So,
yep.
Is local explainability something you think is ubiquitous in everyday decision making? That's part one. And then I feel like the focus these days is on global trends, large-scale analytics. The local explainability and a deep dive into someone like Mark is interesting. Do you see SHAP values as a key feature in decision making?
Very, 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 very interesting question. So basically, I think the question is more or less how is really local explainability useful? And I want to touch on two things. One is, once again, the regulatory requirements. So it might not help on everyday decision making, but if you're building machine learning models that impact life of individuals directly, such as access to credit, access to loans, well, insurance decisions, etc., then your models will be required to be explainable. So maybe you will not use it ever for any decision, but if you don't have the right explainability capabilities, at some point, I believe you will not be compliant with regulations any longer. And to the first part of the question, I don't see it directly involved in decision making, but I can give you an example from the experience at my company of why it makes a difference. It makes a difference in building trust, and in this case, it's internal trust in the company, but why not? It could be trust towards our customers as well. We are a company where we offer a B2C service, and many of our employees are also customers of Moneyfarm. And what happens is that our customers' employees, they use the platform in a weird way because they test new features, they test a lot of stuff. So they have abnormal behavior. And this abnormal behavior is often picked up by the predictive models. So it happens that our customer employees would end up in churn prevention funnels without any real reason of them being considering churn. And this happened actually yesterday. And we got the question, why did I receive this churn prevention email? I'm not considering any churn. And the ability to present this person with what we call score drivers, so the features, the reason that calculated the score for this person, that were actually demonstrating, look, it's platform usage. You do a lot of views, you do a lot of logins, you do a cash flow every other day. That's why the model thinks there's something wrong with you. This really creates a strong trust internally, and it makes other teams of the company really trust the output of predictive models.
All right. Next question we have is, have you had a chance to explore alternatives knowing that it is computational expensive?
Alternatives to the solution for the computational expensive issue. So in this case, to be honest, what I would do is two options. Option number one, try with the inbuilt optimizations and approximations functionalities that the SHAP package has. Option number two, should this not work, I would go straight to sampling the data set I'm working with and training an explainer on a smaller data set. I don't think there's any way out of this. Maybe option number three or option number two can break down into two sub options: sampling rows or sampling columns. So removing features. But then if you remove features, no, that would not really work. That would have to be a full feature selection approach on the whole model.
All right, I think we have time for one more question. Does SHAPly have to be run on the entire data set, or can I run it row-wise to speed up explainability?
No, very good question. It does not have to be run on the entire data set. So, for example, something we do in our scoring procedures, we only run SHAP explanations for the high scored customers. So those who happen to be in the top 2% scored customers. And this is exactly to speed up procedures. Also in the training procedures, it depends, of course, on the volumes of your data. I would always suggest try on the full data set. And then if it takes too long, reduce sample 50%, 70%, 80% of that data set and find that sweet spot where the computational time is for you acceptable, but you don't lose too much on the quality of the explanations that you get.